this would be a perfectly reflective substance. You can imagine that there would be a substance which would be perfectly absorptive. Right? Just nothing gets reflected. Very hard to find something like this in real life that's not a black hole. This is what black holes do, though, right? They don't reflect anything, they absorb it all. Okay, so both of these objects will have a radiation pressure exerted upon them. But it's a different pressure. So let me remind you of something you probably talked about in 16, or maybe not, it's fine. But in the idea of an impulse, right, you gotta go way back into mechanics for this. An impulse is the right language we use when we're talking about a change in momentum. Right? Talking about a change in velocity, we'll say acceleration. Talking about a change in energy, we'll say work. Talking about a change in momentum, we'll say impulse. Same exact system, we're just talking about it in 3 different ways. But what you may have found is that if you have a ball that is incident upon an immovable wall, so this is some mass, some velocity, and we'll let this be the situation where the ball has a perfectly elastic collision, doesn't lose any momentum to the wall, just bounces right back with the same momentum mv. It could be negative mv now, right? Because it's a different direction. But this is one possible situation. Something close to this happens when you're playing pool. Not exactly, but it's close to it. But there's another situation which you could maybe imagine you throw a ball at a wall, and this ball is made of like Play-Doh, or maybe something even softer like bread dough, and it just sticks to the wall. Right? So it comes in with mv, and for the sake of argument, we'll let this be the same m and the same v in both these situations, but it sticks to the wall and has a velocity of exactly 0 afterwards. The question is, which of these receives the greatest impulse from the wall? What's your intuition? Maybe it helps if I remind you what impulse is. Impulse, which is also symbolized with an I, it's a different I on both sides of the board, is equal to the delta of the momentum, the difference in the momentum. Which one receives the greatest impulse?
When it stops.
Who thinks the top one? Raise your hand. Who thinks the bottom one? Let's see if you're right. Delta P for this. Well, delta P is going to be mv initial, final minus initial, right? So minus mv is your final, minus initial, minus mv for a grand total of minus 2 mv. What about this one? 0 minus mv for a grand total of minus mv. By magnitude, which one had the greatest impulse? One on the top. Anybody ever play paintball? Anybody ever get hit by one that didn't explode? Hurts like hell, right? That's why. The impulse delivered to your body by the ball is greater if the ball doesn't explode. If it hits you and splatters, it hurts a little bit, right? If it bounces off, it actually hurts significantly more. That's why. There's a greater impulse because the ball bounces, right? That's why if you take a steel ball and a ball of Play-Doh that have the same mass, and I throw it at you with the same speed, the steel one's gonna hurt more. Just, it's not gonna be perfect like this, but it's not gonna deform, it's gonna bounce off of you where the Play-Doh will deform and it's gonna stick to you, right? It's the same mass, the same velocity, but the steel one is always gonna hurt more because of this. Okay, what in the world does this have to do with light? Well, look at the situation here. It's really similar. Light bounces off this reflective material. It absorbs into this absorptive material. Something really analogous happens here. The impulse, and there is an impulse because light turns out to have momentum as well as energy. See quantum mechanics for details, right? The impulse delivered to the wall, or to whatever this thing is, by the light beam, turns out to be twice as much here as it does here. Your book summarizes this with this expression. Radiation pressure is equal to I over C if we have a perfect absorber. 2I over C for a perfect reflector. So, perfect absorber is this guy. A perfect absorber means it doesn't reflect at all, right? It is 0% reflective. And you can say 100% absorptive, but I kind of like to keep it just in terms of one thing, right? So we'll say that this is 0% reflective, this is 100% reflective. So the momentum pressure, the radiation pressure, turns out to be twice as much for this guy as it does for this guy. So what we can do with that is a little shortcut. If you can tell me the percentage of reflectivity that an object has, I can calculate the momentum pressure if I know how intense the light is. Okay. So let's do a quick example. We'll say we're dealing with light that has an intensity of about 1,200 watts per square meter. That's about the intensity of the sun at the surface of the Earth. It's a little low, but somewhere around 1,200 watts per square meter. We'll say that it's incident upon an object with an area of 2 square meters. And we'll say that this object is 70% reflective. And my question is, how much force gets applied to this thing? Now, I'll just ask about the pressure. What is the radiation? You can calculate the force, if you would like. What is the radiation pressure exerted on this thing? Let's see if we can match up what's happening here. Well, it's neither perfectly reflective nor perfectly absorptive. But look what's happening here, right? 0% reflective, that's what a perfect absorber is. 0% reflective gets you 1 times I over C. 100% reflective gets you 2 times I over C. You can see the spectrum in there. 70% reflective, what do you think is going to be the coefficient here? If it's 1 for 0 and 2 for 100, what do you think it's going to be for 70? 1.7. Yeah, this is how it works. 0% gives you a coefficient of 1 here. 100% gives you a coefficient of 2. 70% reflective will give you a coefficient of 1.7. And just 70% in between. 10% reflective gives you a coefficient of 1.1. Be careful though. What about 90% absorptive? What does that give you? 0.1, right? Watch the language. Because 90% absorptive is 10% reflective. See where I'm going here? Alright, so for this, it's really simple. P is equal to, if I just look at that, 1.7 times I over C. I'm going to equal from this. That is 1.7 times 1,200 watts per square meter over the speed of light, which is about, I'll use 3. Your formula sheet says 3. 3 times 10 to the 8 meters per second. It's closer to 2.99. Cool. I get about 6.8 times 10 to the negative 6. What are my units? What type of quantity is this? Pressure. What are units of pressure? Pascals is what we're using here. Newton per square meter, commonly called a Pascal. Yeah. really small. This is why you don't notice it. It's why the sun doesn't knock you down, right? The heat might knock you down in the summer. The sun itself doesn't, right? But you can then calculate the force on this guy, right? Multiply this by 2 square meters. If this is the force per unit area, multiplied by the area, you get the force out of this. It's going to be tiny. I mean, what's that? 2 times this, I can do that in my head. It's going to be 13.6 times 10 to the negative 6, right? Newtons. That's tiny. That's why you never notice it. But it's not, that doesn't mean it's not there. In my research, when I was researching, I just teach now, which I'm happy. We looked at dusty plasmas. So you make a plasma and you put dust in it, right? Physicists aren't the most imaginative lot. Has lots of applications for space physics, because space has lots of plasmas and has lots of dust. One of our challenges was we would create sheets of dust. The dust picks up charges. If you know what a plasma is, it's an ionized gas, highly ionized gas. So you've got a bunch of charges running around that are dissociated. You've got a bunch of electrons. Electrons would collect on the dust. You make the plasma with an electric field, and so you can find a balance where you just levitate your dust. And then we would illuminate that by taking a laser beam and spreading it out and illuminating a slice of the dust. The challenge with that was the dust is so tiny that if your laser is too powerful, it moves it, and then you can't take data that way because you are affecting your experiment. So this is something I have to deal with a lot. If you ever go into any space physics, you have to deal with this because radiation pressure on small particles can be quite significant, right? We're not going to know, you and I are not going to notice it in everyday life, but it's a thing. Questions about this? How we got it? Where we get these numbers? Anything? All right, so that's the last thing I wanted to talk about from chapter 16, which means the last thing to talk about from volume 2 of University Physics. Any residual questions over this stuff? I should say this particular is not going to be on your exam on Friday. Your exam will be based on your homework. So use that as a guide. Mostly Faraday's law of induction. I'm just dropping everything today. Cool. Any questions about that before we close this book and move on to the next one?
Are we gonna have a quiz for lab?
You will have a lab quiz tomorrow. I'll put the information for that out in an email later.
Okay, thank you.
Any other questions?
Is the exam going to have any energy density stuff?
Doubtful. The question was, is the exam going to have any energy density stuff? I can't imagine. Other questions? All right, then let's shift gears. We've been talking about light as a wave, right? I made an approximation a while ago when I was talking about reflectivity of light as a ray. What does that mean, right? We've all heard the expression ray of light. Well, it is just an approximation. It's the idea that we can represent light not as a wave, although it is a wave, but we can represent it as geometrically what we call a ray, right? What you can think of a ray of light as being is sort of a collection of equivalent points on adjacent cycles of a bunch of waves, right? So there's a wave propagating, a wave. I'm just going to pick out some point, like maybe the peak of all of those waves, or maybe a peak of all those waves, and just draw a line through it. You can think of it like that, but you really don't even have to think of it like anything. We kind of understand what a ray of light means intuitively, right? Because we've seen light coming in through a window, right? That's kind of what we're talking about here. It's just an approximation, but it turns out to be a really useful approximation if we're going to start studying how light moves around and how it bounces around and how it interacts with different media. So this is the section of the course called geometric optics. Geometric because if we're treating light as a ray is a geometrical quantity, and we can see how it moves and how it changes. Okay, a couple things to get out of the way first. We've alluded to this. What is this? You're almost right. So a lot of you said speed of light. It's the speed of light in vacuum, right? Most of us have grown up hearing the speed of light is a constant, and that's true. That is true. It's a constant within a particular medium. And by medium, I mean whatever the light is propagating through. For instance, in this moment in time, the light from these light bulbs is propagating through air, right? The light from the sun propagates through space, and then it propagates through our atmosphere, and then it propagates through the material of your eyeball and the vitreous humor inside your eyeball. It's propagating through different media. The light from inside this room is propagating through the air inside the room, and then through the glass, and then through the air, and so on and so forth, right? So constantly light is changing media. The speed of light turns out to be medium specific. That's with any wave. The speed of any wave is medium specific. Speed of sound in air is not the speed of sound in wood or steel or water. So the speed of light in vacuum is what we call this. It is about, like I said, 2.99 times 10 to the 8 meters per second. Really freaking fast is basically how we read that, right? Really fast. We usually approximate it as 3. For the purposes of this course, this is going to be the speed of light in vacuum and air. It is not quite the speed of sound in air. It slows down a little bit when it goes to air, but only like a little bit. The point being, though, we consider air to be basically a vacuum for these purposes. It is definitely closer to being a vacuum than it is to being, say, a piece of glass, if we're talking about density. So the speed of light is material specific. This is also the fastest light is ever going to travel. In a vacuum, it moves the fastest it's ever going to travel. If it goes into another medium, it slows down. Now, from that medium, it might go back into a vacuum and speed back up. But the fastest it's ever going to go is right here. So C represents a maximum value. Turns out that a useful characteristic for us, if we're talking about different materials through which light may propagate, is to define a new quantity, n. This is lowercase n. I know we use lowercase n's and uppercase n's for a lot of different things. So this is not a number density like you may have seen in chemistry, or a turn density like we did in solenoids. This is a different n. This is called the index of refraction. We'll talk about refraction as we go on. It's defined for any material, three letters means define, as c, the speed of light in vacuum, divided by the speed of light in the medium, which we'll say is v. So speed of light in glass is lower than vacuum. In diamond, it's even lower than that. Oil, water, whatever light is getting. Now, if you believe me when I say that the numerator represents the fastest it's ever going to go, that means necessarily the denominator of this, no matter what material we're talking about, is always less than the numerator. So this fraction is always what? Bigger than 1, less than 1? You say it out loud. Bigger than 1. Yeah, this is always bigger than 1. 1 represents a minimum value here. If the index of refraction of an object is 1, it's not an object, it's a vacuum, right? Because you got C over C. This is always bigger than 1. But interestingly enough, the size of the index of refraction tells you something about the speed of light in that medium. As light slows way down, this fraction gets bigger, right? That's how fractions work. The smaller the denominator, the larger the value of the fraction. So the higher the index of refraction, the slower light is moving in that medium. So if I tell you, okay, in glass, or I should say glass has an index of refraction of about 1.3. Diamond has an index of refraction of about 2.4. In which material does light move the slowest? And you would say diamond, because it's got a bigger index of refraction. Notice though, if I tell you the index of refraction of glass or diamond, you know enough now to tell me the speed of light in that medium, because you always know C, and I've told you N, you can just rearrange to find for the speed of light in that medium. Okay, and we'll do that, that's important. All right, so that's the background information, the idea that light changes speed as it enters into that in the back of your mind. Okay. Well, if light is changing in media, I'll write this down. There is necessarily a boundary between any two media. Media is being the plural of medium, right? There's a boundary. If air is a particular medium that light is propagating through, and glass is another medium, there's a boundary between the air and the glass. It's just right here at the surface of the glass, right? There's a boundary between the air and my eyeball when that light enters my eyeball, right? This is just common sense. But there are boundaries between the media. But the boundaries turn out to be important because what light does as the boundaries determines a lot of things about physics. We'll say this. At any boundary between media, and when I say boundary, that's what I mean, between media of propagation. At any boundary, we expect a percentage of the light to be reflected back from the boundary and a certain percentage to be transmitted into the new medium. This happens with every wave again. Now, one of those percentages might be 0. You might get 100% reflection and no transmission. You might get 100% transmission and no reflection, although that would be very strange. But one of them might be 0, but in general, we expect a percentage to be transmitted and a percentage to be reflected. Again, it's the same thing with sound. If you don't think that sound is reflected, can you still hear me at this moment in time? Yeah, you can, because my voice is bouncing off the wall. It's also bending around my head, but that's okay. The majority of what you were just hearing was a reflection, right, off of the thing. Now I could go into that other room and yell, and you could still hear me. Why? Because that sound wave would be transmitted through the door into this medium. So this is stuff we see all the time. Okay, what happens at the medium? Well, I can show you this in just a few seconds. Where is that one? Sorry, you're trying to make a radio scene, aren't you? There you go. Okay. So I have here, this is a big piece of lucite, basically nice plexiglass. I have a laser, right? Light is going to be propagating through air when I shine this laser on the lucite, and it's going to be incident upon a boundary with the lucite. Right? So I'll show you that in just a second. Good old optical fog. All right, where are you? Never remember this stupid light. There we go. And let me shut this off.